Hi everyone, it's Coach Fred here. And again, I keep saying that everything is my favorite unit, but we are now getting ready to start logarithms and it is my favorite unit. So I hope you like it as much. So we have been talking about that the inverse of an exponential function is something called a logarithm. And we did a little investigation that kind of helps us understand what a log is. And our investigation kind of looked like this. I said 2 to the heart 8. And I said the heart was the log. And so you all were actually able to tell me that the heart was equal to 3. So I think that really tells me in the most simple terms what a log is. It's really the power that is needed to make a certain number. So in this case, the power 2 needs to get to 8 is 3. And so I've said it a couple different ways. A log is the power to which a number is raised to get another number. And so when we look at it, the way we write it is going to be really important so that you understand. So the formal definition is that if we let b and y be positive numbers and b can't be 1, then the log of y with base b is going to be written as log base b of x. So y equals log base b of x, where we call this the base. We call this the argument. And remember that the graph told me that the argument has to be greater than 0, right? The graph of the log function looked like this. And so we had that vertical asymptote showing us that x's need to be greater than 0. And we could also write this as if we wanted it as the base to the y equals x. So remember I said it, we call it the fish hook or around the world. So b to the y equals x, which is why it's the inverse of an exponential, because we normally write our exponential functions as b to the x equals y. All right, so let's play around with this because we do have to get used to the form. So 2 to the 5 equals 32 is what we would refer to as exponential form. We would call 2 the base, and we would call 5 the exponent. Well, in log form, 2 is the base, 5 is the exponent, and 32 is the, let me hear it, the argument. And we're going to need to be able to go back and forth between these two forms. So let's look at how we might do that. So let's look at how we would do that. So if I want to rewrite this exponential a as a log, I would write it as log base 2 of 16 equals x. So you can see that if I were to go around the world this way, 2 to the x is 16. So you can see how they kind of go back and forth. Now it gets tricky because this is an equation, so the equation doesn't have a y in it, and you're like, Coach Fred, the function has where x is as a y, but we're using the values on the screen to kind of help us. All right, let's try the next one. The base is 3, so log base 3, so 3 to what power gives me 81? So 3 to the x gives me 81, so you can see how they're connecting. So log base 5 of 125. So that's actually asking, if I think about what power is needed for 5 to make 125, right? Log base 2 of 1024 equals x. Now we could solve all these, right? 2 to the 4 is 16, 3 to the 4 is 81, 5 to the 3 is 125. Oops, and that should be a 4. 2 to the maybe is 8 is 1024. I can't remember. And then this last one, this is where we talked about the other day when it's a log base 10. This is like we call it the common log, but I like to think of it as like, when we just write x, there's a hidden 1 in front of it, right? Like the standard x. And when we do a square root, there's a hidden 2 right there, right? So with logs, when it's a base 10, we don't actually have to write the base. So we could just write this as log 2580 equals x. So there's a hidden 10 right here, but we don't have to write it. And again, we call that the common log. All right, let's work backwards. Let's write each exponential in log form or vice versa. All right, so 25 to the 1/2 equals 5. Okay, so let's try that. Log base 25 of 5 equals 1/2. Okay, now I want to go log to exponential form. 7 to the 2 equals 49. That's a true statement, right? 25 to the 1/2 power equals 5. All right, 6 to the -1 equals 6. Log base 6 of 1/6 equals -1. And that's a true statement, right? 6 to the -1 power equals 1/6. All right, I wrote log base 10 of 10 here. I want you to really think about this. When these values, when the base and the argument are equal, well, we're asking 10 to what power gives me 10? It would have to be 1, wouldn't it? And so that's a property that's going to be really important. If I give you, I don't know, log base 2 of 2 to evaluate that, that's 1. If I give you log base 35 of 35, 35 to what power gives me 35? 1. So it's a property that's going to be really important. It's kind of like our math fact for algebra 2. All right, this last one, again, has a star because we'd write this as 5 to the 0 equals 1. Right here, we would have written this as 10 to the 1 equals 10. Well, anything to the 0 power equals 1. So we want to notice when the argument is 1, right? When the argument is 1, it meant we raised whatever the base was to the 0 power. And so that will be really important for us to be able to evaluate that log. So if I give you log base 6 of 1, the answer would be 0 because 6 to the 0 is 1. Okay? All right. I'd like us to try and now evaluate. Evaluating logs without a calculator, you have many ways. We could do it like really algebraically, which is just a process, or you could say to yourself, what does a log mean? So if I say, what does a log mean? I'm going to say 7 to what power gives me 49? So come up with an answer. Well, 7 to the 2 power gives me 49. If you need an algebraic approach, you can set the log equal to x and write it exponentially. 7 to the x equals 49. And make the bases the same. So 7 squared would be 49. So x would be 2. So that's like an algebraic approach if you really want to be sure. Or again, let's try this one. 2 to what power gives me 16? I think at this point you're seeing 2 to the 4 power gives me 16. So my answer is going to be 4. But if you need an algebraic approach, set the expression equal to x, write it exponentially, and solve. 2 to the x equals 16. Now, this is what we've been practicing even with exponential equations, the process of making the bases the same. That's what you're doing if you do the algebraic approach to evaluating a log, right? Because 2 to the x equals 2 to the 4. So x equals 4. Now, you might not need to do this when they're easier logs, but if they get more challenging with lots of steps, perfectly acceptable approach. So like on this one, 2 to what power gives me 1/8? That might be pulling a lot of cognitive load from the brain, and you might just say, you know what, I'm going to make this easy. I'm going to set it equal to x and write it as 2 to the x equals 1/8. So then you can visually see what's happening here, right? We need to make the bases the same. Oops, I don't like that one. We need to make the bases the same, so I'm going to write this as 2 to the x equals 2 to the -3. Remember, 1/8 is 1/2 cubed, and then I want to make the bases the same, so I would have to bring it up and make it negative, so this would be -3. All right, log base 5 of 5 to the 1/2. So this one's a little bit trickier. So I don't want it to be, though. So I'm going to do the algebraic approach. 5 to the x equals 5 to the 1/2. Okay, so this to this equals that whole expression. So we can see that x equals 1/2. Now, later on, we're going to learn that there's actually a property of logs. I'm going to show it to you quickly now that tells us, and it's like a process that power, we can actually bring it down to the front of the log. So we could write that as 1/2 log base 5 of 5. And then evaluate this part. And we know that any log of base with the same argument is going to be the number 1. So that's another approach to getting 1/2. Okay? All right. Let's try another one. Log base 5 of the square root of 5. All right, so 5 to what power gives me the square root of 5? Well, algebraically, 5 to the x equals the square root of 5. To make the bases the same, we're going to say 5 to the x equals 5 to the 1/2. All right, so I'm going to suggest you try these next 3. So press pause and come back and see if you've got them. Okay, so you can see Coach Fred, hopefully you had to use your brain a little bit, and Coach Fred gave you some harder ones here. So I used the algebraic approach on F rather than just saying the definition to myself. And I got that x was 1/6. So 6 to the x equaled the 6th root of 6. I wrote the 6th root of 6 as 6 to the 1/6. And so once the bases were the same, they canceled. I put the 2 properties we talked about in an earlier video on here. So if we did this algebraically, 7 to what power gives me 1? And we know if the argument is 1, the log will always evaluate to 0. And then the last one, we really have to think analytically here about the graph. Remember, the graph of a log has a vertical asymptote at x equals 0. So the graph always is going to be greater than 0 unless it's translated left or right. And so the argument can never be negative, so that would be no solution. Okay. I know that was a lot packed into a short video, and I really appreciate your attention. I think it would be really helpful for you to sometimes go back to this just to make sure you understand what a log is. But to reiterate, you're asking, a log is the power to which a number is raised to get another number. So it's the power a number is raised to get another number. Okay? All right. Hopefully that was a helpful video. Have a great day.